Hello everyone, my name is Mohammed and today I will be presenting you assignment 3 machine learning. This assignment is easy to follow yet needs the patient to solve each question at a time. So this assignment is divided into two parts. Part A, we will be running pre-coded cells to see and understand how convolution 2D kernel works. And at the end, we will respond to question 1 and 2. Part B, same, we will be running the pre-coded cells and we will train the given neural network and then we will respond from question 3 to 10. And part A, here we are given pre-coded. We are importing here necessary packages and libraries. Here we are getting the image from this URL. Here we are visualizing the content of the response and we are printing. And here we are plotting our first image. Here we are printing the shape of the array. Here we are comparing the values of color, canals 0 and 1. Here we are comparing the values of color 1 and 2. And as I mentioned, this code already been given from our professor. Here we are saving the color canal and we are plotting here and we are showing the image. As we can see here that this image is displayed in a grayscale because we have only one color, color canal. Here we are visualizing the values inside of the resulting array. Here we are creating a barred array. Here we are creating the kernel. Here we are creating output array filled with zeros. And then we are comparing both arrays, the original array and the padded array. And here we are applying the kernel to array where we are looping through. And here we are plotting our result. Here we are defining a function to squish out the values. Here we are defining a function to apply a convolution 2D line detection. Here we are creating a horizontal kernel and then we are applying the kernel to the image and we are plotting. And here's the image. So this is our part, question 1A and B. Based on the kernel represented on the above image, create a kernel to detect 45-degree lines. So I defined my kernel like this to detect 45-degree. And then I start applying the kernel to the image. And then I plotted. Question 1B, based on the kernel represented on the above image, create a kernel to detect 135-degree. So here I'm creating a kernel to detect 135-degree, and then I'm applying the kernel to the image, and then I'm showing the image. Question 2. So this is pre-coded, our professor gave us. So all we have to do is to apply the kernel and then plot. And I plotted, and here's the image. Question B, age kernel 2. This code was being given before, and here I'm applying the kernel to the image, and then I'm plotting the image. As you can see now, the edges is a little bit visible than the previous one. And here we're number C, question number 2C. This code is being given to us. All I had to do was to apply the kernel to the image and then plot. And 2C, as we can see, the edge is more visible than the previous ones. And here number D, I added this one. I was having fun, and I added this line to see the car. Part B. So now we are in part B, where we will be answering from question 3 to 10. So as usual, we are importing the necessary packages and libraries. Here we are asked to load our dataset, and then we are using one hot encode target values, one for train labels, and one for test labels. Here we are converting the train images from integers to float, and here we are normalizing to range 0 to 1. And here we are building our neural network. We are creating the model. So the first layer is 2D convolutional layer, which has 32 filters, each with size of 3 by 3 pixels. The padding is set to same, which adds padding to the edges of the input images to preserve its spatial dimension. And here we are using activation ReLU. The kernel constraint argument is set to max norm 3, which constrains the maximum norm of the weights in each filter to 3, helping to prevent overfitting. The input shape argument is set to 32 by 32 and 3, which means the input image is 32 by 32 RGB image and 3 color canals. And the second layer is max pooling layer, which reduces the spatial dimensions of the input by taking the maximum value within 2 by 2. The third layer is flatten, which takes the output of the previous layer and flattens it into one-dimensional array, which can be passed to fully connected layer. The fourth layer is a dense layer with 128 neurons, which is fully connected to previous layer, and we're using the activation ReLU activation. And for the fifth and final layer is another dense layer with 10 neurons, which is fully connected to the previous layer with activation function, softmax function, which outputs a probability distribution over the 10 possible classes. And here we are compiling our model, and here we are showing the summary of the model. And here we are creating a function for the custom callback. That's for login. And here we are initiating the custom callback. Here we are training. Excuse me. Here we are train our network with train images and train labels using EPAC 50 with patch size 256. Here we are defining a function to plot the result, and then later on we will be using the result plot to see the output. Okay, question 3 to 10. Did the network presented a sign of overfitting? If so, which epoch? To check if the network presented sign of overfitting, we can plot the training and validation accuracy over the epochs. If the validation accuracy starts decreasing or staging while the training accuracy keeps increasing, it is a sign of overfitting. So in our case, the overfit data was around epoch 20 as the training accuracy kept improving while the validation accuracy reached a plateau and started decreasing slightly. Question 4. Write down how many layers this model has and identify their types. So this model has 5 layers. The first one is convolution 2D layer with 32 filters of size 3 by 3 with same padding and ReLU activation function. Second one is max pooling 2D layer with a pool size of 2 by 2 flattened layer to convert the two-dimension future maps into one-dimension future vector. And the next one is a dense layer. So 1, 2, 3, and the fourth one is a dense layer with 128 neurons and ReLU activation function. And the last one is dense layer with 10 neurons equal to number of classes in the CIFAR 10 dataset and softmax activation function as we see in it here. Activation function. Okay, number 3. Number 3 we answered. Write down how many. Okay, we answered this one. Okay, number 5. Briefly explain what is the purpose of each of these layers. So for convolution 2D, this layer is used for performing convolution operation on the input images. It extracts features from the input image by sliding a filter over the image and computing that products of the filter and image patch. The output of this layer is set of future maps which represent the presence of certain features in the input image. Second one is max pooling 2D. This layer is used for downsampling the future maps obtained from the convolutional layer. It reduces the spatial dimensions of the future maps while retaining the most important information. This helps in reducing the competition complexity of the network and makes it more efficient. Third one is flatten. This layer is used for flattening the output of the convolutional and pooling layer into one-dimensional array. This is required before feeding the output to the fully connected layer. Fourth one is dense. This layer is used for performing matrix multiplication between the flattened future vectors and set of learnable weights. It applies a nonlinear activation function to the output of the matrix multiplication and generates the final output of network. Softmax. This layer is used for converting the output of the final dense layer into probability distribution of the different classes. It ensures that the sum of the probabilities of all classes is equal to 1, making it easier to interpret the output of the network. Number 6, add one or more convolution layers to your model and run it again. So here we are creating our model. This time we are using 64. And then we are compiling our model using Atom as an optimizer. And then we are training our network. After each epoch, the accuracy of the model is computed both on the training set and on the validation set. The training accuracy indicates how well the model is fitting the training data, while the validation accuracy indicates how well the model is generalizing the new unseen data. At the beginning of the training epoch 0, the training accuracy is low, 47%, while the validation accuracy is slightly higher, 57. This suggests that the model is not yet fitting the training data well and may be underfitting. As the training progresses, both the training and validation accuracies increase. The model seems to be fitting the training data well after about 10 epochs. As the training accuracy reaches 89%, while the validation accuracy is still improving. However, after epoch 15, the validation after epoch 15, the validation accuracy starts to plateau and even slightly decrease, while the training accuracy continues to improve. Here we have 97, and here we have 67. Overall, the model seems to perform reasonably well, achieving the maximum validation accuracy of about 69%. However, there is some evidence of overfitting. So if we want to try some regularization technique, such as dropout or other hyperparameter tuning to improve the model's performance. Compare the result and describe what are the differences between them. So explaining, by adding one more convolution layer to the model, we have increased the complexity of the model, which might help in capturing more features from the images. After training the new model for 50 epochs, we can see that the validation accuracy has improved compared to the previous model, reaching up almost to 70%. This is improvement over the previous model, which reached only 64 validation accuracy. However, the new model seems to be overfitting after around 20 epochs. As the training accuracy continues to improve while the validation accuracy plateaus and then decreases. This suggests that the model is fitting the training data too closely and not generalizing well to new data. Therefore, we may need to consider adding regularization techniques or reducing the model complexity to avoid overfitting. Number 8, add a dropout layer to your model and rerunning again. Here we are creating our model. We, we add the dropout layer after the max pooling layer, and we set the drop rate to 0.2. Setting the dropout 0.2 means that 20% of the input units to the dropout layer will be randomly set to 0 during training, which helps to prevent overfitting. The value of 0.2 is commonly default value used for dropout layers, but it can be adjusted on the specific problem and performance of our model. And here we are compiling our new model. We are using optimizer Atom here and accuracy as a matrix. And then we are training our model. Okay. And then we are calling the result plotting. So as you can see, our validation accuracy is a little bit improving. Explain with your own words what is the purpose of dropout layer and how it works. Okay, a dropout layer is a regularization technique used to prevent overfitting in a neural network. It randomly selects a set of neurons and drops them out of neural network during each training iteration. This has the effect of reducing the interdependencies between neurons and forces the network to learn more robust features. The dropout layer works by reducing the co-adaptation between neurons in the same layer, thus avoiding the overfitting issue. It randomly sets the input units to 0 with a probability of p, which is hyperparameter specified by the user. This means that the input to the next layer is randomly some sub subsummed version of the input to the current layer, and the network learns to be more robust to the variation in the input. Number 10, make any other modification. Okay, number 10. Here we are loading our data set and we are splitting into train and test sets. And then we are here we are pre-processing the data by slicing it between 0 and 1. And then here we are defining our matter architecture. And here we are compiling our data. And then we are training. As you can see, I I made it the epochs to 50 and then rerun it. This code it starts from 96, and here we have improving. We run C overfitting here. It is keep improving 97 until epoch 50. Our test accuracy is 97 here. And here we are we are calling our result plotting. I repasted again the result plotting from part B. Somehow the result plotting was not working for me, so I had to repaste because I didn't want it to rerun again my 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 output. Yeah, so here we see it improved well if we compare to the others, our validation accuracy. Thank you for watching. See you next time. Bye.